Welcome students! Today we'll be learning about electron configurations. So just what are electron configurations? Well, it's basically the order in which electrons fill the theoretical energy levels within an atom. The rules regarding electron configurations play directly into an element's position on the periodic table, but we'll get into this later. Before we dive deeper into the electron configuration of atoms, we must understand a few principles. The Aufbau Principle states that electrons in their ground state fill orbitals of the lowest energy level. Due to this principle, the single electron in hydrogen, as you can see here, goes here at 1s and not 2s or 2p or anywhere else in this table. In its ground state, it's always going to be in 1s. The Pauli exclusion principle states that a maximum of 2 electrons can occupy an atomic orbital, and they can only do this if they have opposite spins. Therefore, the electron configuration on the left is incorrect, but the one on the right is correct. In fact, the one on the left is actually impossible. Keep in mind that the arrows represent the spin on an electron. This will be important later on. As you can see, there's currently 3 electrons in this theoretical configuration I have over here. This would be incorrect, as all of them have the same spin and they're all occupying one orbital. Over here this would be correct. There's only 2 electrons in these orbitals, and they all have opposite spins. The final rule we will learn about is Hund's rule. This rule states that every orbital must be filled on that energy level before electrons will pair up inside of the orbital. As such, the table on the left is incorrect, and the table on the right is correct. Keep in mind, again, the direction of the arrows represent the spin of an electron, and electrons with an upward facing arrows always come first. So, as you can see, the ones on the left are incorrect. As we paired these up, these would not pair up in an actual table. Instead, you would have something more like this, and this is for nitrogen. Just keep that in mind. So 7 electrons, 1, 2, 3, 4, 5, 6, 7. Over here, this is wrong, as these 2 electrons would not pair up. Following these rules, you can create a sort of hierarchy as to where electrons go within an electron table. As you can see, electrons will prefer to have an orbital by themselves than to share an orbital, as you can see here. And they would rather share an orbital than have to move up an energy level. So following this chart, you can pretty much figure out where any electron goes within the table. Energy levels in electrons are denoted by a number and a letter, S, P, or D, and sometimes F, but we're not going to get into that for the purposes of this video. S orbitals can hold 2 electrons, P orbitals can hold 6 electrons, and D orbitals can hold up to 10 electrons. The denotation of these energy levels changes based on the number of electrons in the orbital. For example, if there were 3 electrons in the 2p orbital, it would be denoted as 2p to the third. Now for the difficult part, where we put it all together. At the start of this video, I mentioned that electron configuration played a large role in an element's placement on the periodic table. Here I will explain how this works. You already know that electrons fill energy levels only if all lower energy levels are filled, and that these energy levels are represented by a number and a letter. These letters and numbers determine an element's placement on the periodic table. So for example, lithium fills all of 1s, all of the 1s orbital, as you can see right here. And it has 1 electron in 2s. So we know to look at 2s right here on the periodic table. And it has only 1 electron, so we count over 1, which is right here, and that's where you see lithium. Now let's say we had a different atom. In this case, let's say it has 2 electrons in its 2p orbital, which is its highest energy level. Well, to do that, we simply go over to our 2p orbital section of the periodic table and count over 1, 2, and we'd end up at carbon. So this mystery element would be carbon. It's as simple as that. Same thing over here with 3s. Say we had 1 electron in 3s, we'd simply count over 1, and it's sodium. It's simple as that. You just count along the table. As long as you know where each of these orbitals' space is on the periodic table, you can find out how many electrons very easily are in their largest energy level orbital. Hopefully this video gave you a better understanding of electron configurations and how they work. Thanks for watching.